some DOE is always better than no DOE, in my experience.
Yeah, exactly. And in addition to the custom design platform, JMP has incorporated all the many developments and innovations to increase the power and efficiency for specific use cases since DOE first started gaining widespread use back in the 1920s with Ronald Fisher. And one of these innovations is the OML design, which stands for Orthogonal Mixed Level Designs, but actually that's not so important. What's important is that it's particularly powerful at screening many variables at once. So if that's a situation you're facing, then this may be a good option for you. It's new, and today we're letting you know that it's available in JMP. My colleague Jonas will now provide a short introduction to this new design and how easily accessible it is. Jonas, please.
Thank you. So with this short sidetrack, we want to look into the latest developments on screening designs, which are orthogonal mixed level screening designs, or OMLs in short. So first of all, let's have a short recap on screening designs. So designed experiments tend to get very large if we have many factors in our system. So screening designs are used to screen out the important factors out of the big number of unimportant factors in the system. And with these important factors, we usually do optimization designs later on to deeply investigate the system behavior. If we look into the history of screening designs, you might already know fractional factorial designs. These designs are relatively old and inflexible, and they're so-called textbook designs with only 2 levels. With the upcoming computing power in the 90s and the ongoing centuries, definitive screening designs were developed, and these designs showed great properties for screening purposes. So we have 3 levels for the continuous factors. We have analyzed main effects with effects of higher order in the system, and we even have the chance to spot interactions and quadratic effects in the screening phase if we are lucky. These designs are great, but they show that they are not the best choice if you have a lot of 2-level categorical factors in the screening phase, and they're also quite inflexible when it comes to the run size. So today we want to look at orthogonal mixed level screening designs to address these as a DSD alternative. So these designs, these OML designs, have the same beneficial properties as DSDs, but half of the factors are 3-level continuous and the other half are constructed as 2-level categorical or continuous factors. With the first half of factors, we even have a higher power of spotting curvature compared to DSDs, and we have 3 construction methods, which gives us a lot of flexibility when it comes to the number of runs of our design. So let's have a look in a practical example. This is a screening example from the biotech industry with 8 different factors. 4 of them are continuous. 4 of them are 2-level categorical. And the true response function we are looking at has 4 active main effects, which are temperature, RPM, stirring position, and catalyst, as well as 2 two-way interactions between temperature and RPM, stirring position and RPM, and the quadratic effect of temperature. So let's have a brief look on how these OMLs will perform in this kind of situation. So what you see here on the left is the design. We have 4 3-level continuous factors here, 4 2-level categorical factors, and in the end we want to investigate the yield and maximize the yield in our system. This is a design with 16 runs, and let's see how it will perform if we do the analysis in JMP. So what you can see here in the report is that all the main effects are spotted. So we can see that the analysis spotted temperature, RPM, stirring position, and catalyst, as well as the 2-way interactions between temperature and RPM, RPM and stirring position, and the quadratic effect of our temperature. So this is a great result. We were lucky, and we were even able to find all the active effects in the system here. So we can use the profiler to optimize and look how our system works. So if I change RPM here, you can see that the yield is changing, but also that the slope of our temperature curve here is also changing as well. So this is a clear visualization of an interaction going on. And now we can use the profiler to find the optimal settings, which seem to be at a stirring position at the bottom, add a catalyst setting for B and low RPM settings here as well. So if we check for the best yield possible, we will end up with a mid setting of temperature and a yield of nearly 97%. So this is great. We learned how the system worked, and we were even able to optimize with this screening design as well. So how do you actually get these designs in JMP 18? So they're under DOE, classical, vector screening, screening designs here. And if you put in a sufficient number of factors, for instance here, I will put in 6, then you will have a new option if you press continue, which are construct a mixed level screening design here. And as you can see, this gives you 3 different methods to construct these kind of designs, which can cover a whole range of different run sizes from 10 up to 32. Everything is possible. And yeah, you can try it out. It's new in JMP 18, and it gives you a great way to understand your process, to optimize your process, and in the end, to bring your product to market as fast as possible. Thank you.
Thanks, Jonas, for illustrating how a combination of modern methods like OML and modern software like JMP helps you maximize the value you're getting from every experiment you do, ultimately accelerating the speed at which your product and process development can occur. Better still, as Jonas and indeed Owen showed, JMP will present experimenters with the appropriate designs for their specific situation without them having to search for them, allowing their time to be spent on the effective application of DOE to their work. And the other key learning is that DOE is not a fixed method that has been developed for and only works for specific scenarios. In fact, it's constantly being improved, with new designs, as we've just seen, offering better, smarter, faster solutions for new applications.